Hello, hello. So welcome to the session. We will start with Alex. You may have heard of renjin, which is an open source implementation of a subset of R. It's very impressive how far these guys have gotten with such a small company in compatibility, and I'm sure that Alex will tell you more.
Thanks, Thomas. So yes, my name is Alex Bertram. I'm from Be Data Driven. Sort of loud. So I'm gonna give a talk about a new tool based on renjin that it's now a package that you can use. So my goal is that for all of you that are working, writing our code, that this can be an extra tool in your pocket when you encounter performance problems. So I hope to keep it very practical and hands-on. But first, I do want to say just a couple words to introduce the renjin project for those who may not have heard of it. Renjin is a complete alternative interpreter for the R language. So there's what you can call GNU-R, and you can run your code in RStudio or on the command line, or you could take that same code and run it on renjin, for example. So it's built on the Java virtual machine. Our goal was to have something that was a little bit easier to embed in other systems, and also to be able to start with a new code base to kind of play with some optimizations. And the optimizations are really what I'll talk about today. So you can download it from renjin.org, you can run it, you can get a Debian package, a zip file, or you can include it as a Java library on Spark or Flink or any kind of Java-based system. And you can also, you can embed it in databases. It's very flexible in that way. And one of the nice properties of renjin as an interpreter for R code is that it has different ways of working with different kinds of R code. So it's at the base there's kind of just a very plain, simple, what you call AST interpreter, which is a lot like GNU-R, which can handle, or is supposed to handle, everything in the R language. So all of the wonderfully dynamic bits, that's how it handles it. We also have an auto-parallelizing vector pipeliner. So if you do vector operations that are chained together, renjin can see that and parallelize them automatically, put your work into separate threads, so that you don't even have to explicitly parallelize your code. And the last component is it's got a just-in-time loop compiler. That means that if it encounters a loop and it sees that it's a big loop, then rather than try and interpret it instruction for instruction, it will try and compile it on the fly to machine code and make it run faster, right? So the vector pipeliner, for example, can take a series of operations. It can extract a tree to see, okay, I have two means, but they're independent of each other, so those can run on separate threads. All right, so that's one example of optimization. The loop compiler, it takes, I mean, this is the kind of code that's unfortunately a little deadly in R to write, and everyone's told, you know, don't write for loops. But this kind of for loop, it doesn't use any kind of dynamic properties of the R language, so we can really automatically compile that down to first an intermediate form and then down to machine code and run it faster. So it's exactly the kind of code that maybe you might take and by hand rewrite in C or C++. Our goal is to be able to do that automatically so that the everyday R programmer doesn't have to worry about learning a new language or using separate tools. It should hopefully all be automatic and transparent. So together, these two components, they can, in many cases, offer real gains in performance. So this is a paper that's coming out that applies those two components to running a script from the survey package. And you can see that it allows renjin to really scale with much more data across many more threads as compared to the GNU-R interpreter. So that's the good news. The challenge is that we want to build a drop-in interpreter that you can just say, okay, do I want to use GNU-R or do I want to use renjin today? But the reality is that's a very tough goal because there's no standard for the language. There's lots of packages with C and C++ code that do all kinds of funky things that make it difficult to compile and to run exactly the way they were intended. So we're not quite there yet. And what we were thinking about is there still a way that we can leverage these powerful optimizations, like for existing in our existing projects with clients, where maybe we're using useR or a set of packages that don't yet run on renjin, and maybe just run parts of that code, the parts where we have bottlenecks, just run them in renjin. So can we just drop in renjin into an existing workflow? So yes. So you can install renjin now as a package. You just source this in useR. It will download the package and install it. And then you can take, this is a very simple example, but you can take a loop that might run for a minute or longer on useR and just wrap it in a call to renjin, right? So you just take your performance sensitive section. You put it in the middle of a call to renjin, just like you would use local or eval or a local, and you get your result. So it's not quite a completely magic box. I mean, you can't put anything in there because the R language is large and wonderful, and not all parts of the R language are amenable to analysis and this kind of compilation. So things like if you use deparse or eval or source, substitute in a loop, we're not going to be able to compile that. And the goal is to give you, as a developer or as a user, feedback, right? So if I write something like this and I say, okay, for each iteration of the loop, read in a file on the file system and execute it, the compiler has no way of knowing what's going to come next. So it will default to the interpreter. It will still complete the loop, but you just don't get any of the advantages of the optimizer. But you do hopefully get a nice error message or a nice warning that, hey, this code could run faster, but you've got this call to source in the middle of your loop. Maybe you could think about removing that if you wanted to run faster. So this is kind of an experiment to see, can we offer some guidance to our users about what makes your code slow, and kind of guide you towards writing R code that's still R code. It's plain R. You don't have to necessarily learn a new language or use another set of tools, but maybe we can guide you to writing it in a little bit more simple way. So I just want to take a minute and compare what renjin does and what this JIT interpreter does compared to the useR bytecode compiler. You might not be aware, but by now, with all the good work of the R core team, it's now on by default on renjin R 3.4. And so functions are compiled to bytecode before they're executed. And this certainly does deliver some performance benefits, but it has some limitations as compared to this approach. So, I mean, this is typically what the bytecode compiler sees. It might see a function with x times 2, and that looks simple, but you have no idea what x is. X could be an S4 class, X could be a huge vector, it could be a small vector, it could be a double, it could be an integer. You have no way of knowing at that moment, if you just see that function, what's coming next. So there's some just built-in limitations. Now, with the just-in-time approach, basically we don't do any work, we don't do any compilation until we enter the loop. And then the interpreter says, oh, wait a second, I've got another 1,000 iterations of this. I'm going to stop. I'm going to look at all the types that I have. So you know that S is 0, for example, that it's a double of length 1, that it doesn't have a class attribute, that it's not an S4 object. And you can use all of that information to compile this specific execution of the loop to really, just as fast as C++ code. So it's a very powerful approach. And I have a couple of really just, these are dummy examples, but they kind of illustrate where the savings can come from. So this is this simple sum loop, or a sum plus the sum of the square roots. Without the bytecode compiler, it's 25 seconds on useR. With the bytecode compiler, it does come down to 12. But with renjin, it can see that these are all just simple integers. It can put them in registers in the processor, and you have over 25 times speed up. If you add attributes, right, that becomes even more expensive, because now you have x is, or that should be class S is foo, excuses. Class S is foo, then then every time you have that loop iteration, you've got to do a lookup to see if there's an S3 method. Is there a foo.plus? And the GNU interpreter and the bytecode compiler will do that every iteration for thousands or tens of thousands of millions of times. Whereas with just-in-time compilation, at the beginning of the loop, we can do that lookup once and see that there is no plus.foo defined, and we can just pump out the super simple code. If you have function calls, I mean, function calls are functions in R are great. They're the building blocks of abstraction, and they're very flexible. You can have named arguments, you can have optional arguments, you can have argument forwarding, but all of that takes time to actually do. You've got to match the arguments by name. You've got to create a new environment. There's a lot of work that the interpreter has to do just to do that one simple function call. But again, the compiler, if it sees that we're entering a for loop that's very big, it will look up that function ahead of time. It will what's called inline that function, so that it puts it right in the middle, so there's no actual function call. And then again, you get really streamlined, simple machine code. So whereas with GNU-R, this is you might have 200 seconds, 250 seconds to run this loop. The time doesn't really change for renjin because it's able to understand what's really going on. So I can't claim that you're going to get a 200 times speed up on every code that you put into renjin. We're looking for benchmarks, but I hope that this demonstrates the possibilities of this kind of approach. So we've still got a lot to do that we want to do with the compiler. So we want to expand the rules for type inference, right? So the compiler needs to know, right now knows a lot about S3, for example. It knows what happens when you do a call for S3, how to apply that and how to compile it, but it doesn't yet know anything about S4. So my colleague Parham is working on S4 type inference so that S4 calls can also be inlined and compiled. And we're just expanding the rules so that it can be smart enough to know, to understand what happens when you do a subset operation, things like that. Yeah, we'll be adding shortly just-in-time compilation for also a calls to apply. So if you call an apply with a function and the function is amenable to compilation, then that can be compiled and potentially parallelized if it can be shown to have no side effects. And we really want to improve the storage optimizations. So R has copy on write semantics, so every time you change something, in principle, you're making a copy of it. There are some tricks to get around that, but we can do a lot better with the compiler. And we're also looking at adding a kind of parallel backend to this renjin package, because one of the nice things about renjin is that you can share data between multiple threads. So it would give you the ability to run R code in multiple threads in the same process, sharing the same copy of data. So that's a couple things on the roadmap, and now I'd like to open up for questions or comments. Yeah. And please try it out, and if it doesn't work, send us a line. I don't know if you want to stand up or.
I have two questions. One is, do you have plans to do anything with reference classes? And the other, I'm sorry, I came in a bit late, so I'm not sure if you've already answered this, but how does this interact with, say, packages that are byte compiled? Do you need to not have compiled anything to be able to use the renjin compiler?
Okay, so first on reference classes, I believe, but I don't have benchmarks, that if the reference class is not modified in the loop, so if you're only looking at elements in the reference class or doing reference called dispatches, then that will get inlined, but we don't yet have support for understanding changes to reference classes. So on the second thing, no, the bytecode compilation doesn't affect the compiler, because even though you bytecode compile something, the original kind of AST structure is still there, so we can always access that. Yeah.
But it will not take advantage of the bytecode that was there before. It's orthogonal, right? Yeah, well, it's orthogonal, so the R bytecode that is there will be dropped, not used, but yeah, compilation will happen. Yeah, in a different way.
How brittle is the solution when there is a new R version coming out? I remember there are competing solutions which are stuck with 2.5 or something like that.
Yeah.
Is this portable?
No, I mean I think every time a version comes out, we do some updates. But I think it's particularly this compiler. It's relying on all of the functions as they're defined in R. So if there's a new release of of R that includes changes to the stats package or to the base package, all of that code is being used, right? So there's some work to do, but it's in the past it hasn't been a huge amount to make changes or to update it. We started out at 2.14 and now we have compatibility with 3.3 or 3.4.
So I was wondering what is the difference between calling this renjin package from the base R or using your special R version. So is there any difference in doing that?
Is there any difference between
using your R version or to using the renjin package with a usual RGNU?
So the difference between running just if you run the whole renjin interpreter, run all of your code in the interpreter versus running it in the package. Yeah, I mean there's some cost. We have to move data between. It's in the same process, but we have to move data between the GNU-R and renjin. So that's not too bad, but it does introduce a cost. And the one thing is that we can't do with the loop compiler is we can't call into native compiled code in this package. But for renjin itself, we have a toolchain that converts that code to Java bytecode that we can then compile together via the loop compiler. So that's one limitation.
Thanks.
Okay, I can't resist asking how many packages do you support? How many cron packages can run with renjin?
How many cron packages can
How many cron packages can pass their test running on renjin?
I believe about 80% of packages, 60 to 80% in CRAN pass at least half of their tests. The problem is that we use as tests are examples, which don't always complete successfully. On Bioconductor, it's much lower. It's about 20%, I think, on Bioconductor. Yeah.
Okay. Yeah. So there is time for one more question, if anyone has one. Or
Yeah.
So if I try to confuse the, your compiler, like in your loop, if I just add a new plus.foo method or something, is it 100% reliable, or is it possible to trick it like that?
Yeah, one of the things that it does is that after it finishes, it runs a verification to make sure that you haven't done exactly that. Okay. That any of the functions that we've resolved do not get assigned to within the body of the loop. So it's intended to be complete verification. Like, it's not speculative. It's not like, oh, we think this will probably work. We only do optimizations where we can prove that a double plus a double will always return a double. Yeah.
Okay, thanks.
Okay, thank you.